Today we're going to talk about the Einstar 3D scanner. This isn't going to be an in-depth product review, but we're going to talk about some of the automotive-based projects that I've used this for over the past year, and some general thoughts, tips, and tricks that I've learned along the way. So check it out. Welcome to the channel. If you're new here or haven't been following along, my primary project is swapping a Mazda turbo rotary engine into a BMW i8 and retaining the factory plug-in hybrid functionality. That's the plan, at least. Normally a project that's this ambitious would be relegated to sitting on jack stands for months, if not years, while all the fabrication and fitment is figured out. But here we have a complete one-off induction system that's been 3D printed in a mix of nylon, aluminum, and Inconel, and all that was achieved while I continue to drive and abuse the car on an almost daily basis, as well as do some much needed CAN bus data logging that we're going to need to do to support the hybrid system down the road. All of that wouldn't be possible if it wasn't for 3D scanning. So my primary and really only use case for 3D scanning is to design automotive parts. And to get right to the point, after a little more than a year and a little less than $1,000, I can say that the Einstar has absolutely been 100% worth the investment. It has definitely paid for itself multiple times over in both the time and materials that it saved me over various projects over that year. While the Einstar is the first scanner that I've used for any serious amount of projects, it's technically the second scanner that I've owned. The first of which was a RevoPoint Pop 2 that was purchased off of one of their many Kickstarter campaigns. To put it as politely as possible, after receiving my Pop 2, I quickly decided that it wasn't the piece of hardware for me, and I turned around and ended up reselling it after about 48 hours of ownership. After selling my Pop 2, I realized that RevoPoint's business model is launching a product to the market, and then as soon as it's released, firing off another Kickstarter campaign for the next latest and greatest piece of hardware. As an end user, that doesn't exactly instill confidence that the product I'm buying is going to be thoroughly developed or have much support for follow-on improvements after it's released. In contrast, researching Shining 3D, they had an extensive range of commercial-grade scanners upwards of $50,000. The Einstar also benefits from using the same software package as some of their more expensive scanners as well. Now, any 3D scanner is not going to be some magic digitizer of reality. Well, it kind of is, but at the end of the day, it's a tool, and no tool is going to do everything perfectly, and the Einstar is no exception. There's things that it does really well, and there's things that it struggles with. But one thing it does not do well is scanning smaller objects. So if I'm reverse engineering something into CAD or developing an interfacing component, usually my go, no-go as to whether or not I'm going to set up the scanner is if I can measure the part entirely with my 6-inch caliper. Usually anything that's bigger than that, I will break out the scanner even if it's a simple part. A good example of this is a Mockup coil bracket that I was recently provided to create a DXF for so that I could get laser cut in aluminum. It's almost silly to 3D scan a part like this because you can easily measure it, but it does offer the benefit of having a nice quality and sanity check after the fact to make sure that you didn't transpose any dimensions and that the part accurately reflects the ones you're trying to reverse engineer. The whole process of setting up the scanner, making the scan, getting it into Fusion 360, and creating the DXF only took 45 minutes. So there's almost no reason not to scan an item. That way you can always go back and check the data if you have any issues going forward. So the real place that the Einstar shines, no pun intended, is larger projects like developing a turbo kit or a motor swap, where you have a large area like an engine bay that if you were taking manual measurements, you're only going to collect a limited set of data points, and you're inevitably going to forget some critical dimension that you're going to have to trek yourself back out to the garage after you've already invested a few hours worth of design time. It just really disrupts your workflow, and you have to go back and reestablish all your baseline measurements. And when you're trying to measure a complex part like an engine bay, and you're getting dimensions off of multiple axes, you're introducing the possibility to have compounded error every time you're combining multiple measurements. This has really transformed the way that I design parts, and I can create things that fit much tighter than I had previously done before. If I took manual measurements, it was pretty often that I would incorporate slots so that it would offer some aspect of adjustment. That way, if something didn't quite line up with my measurements, I'd still be able to make it fit pretty well in the end use. One of the areas where you'll start to see complaints about the Einstar, or where it'll appear to struggle, is on really large objects, especially if you have an overly fine resolution. If you're going to try to scan an entire car body in a 0.2mm point cloud, you're going to be in for a really bad time. Typically, the complaints you'll see around this type of scan is complaints that the software is going to freeze or crash. Over the past year, I've probably had 2 legitimate software crashes, but the more common problem is that when you're scanning a really large object and then you go to mesh it, the software will appear to get stuck at a 40% progress bar. And at that point, it's time to just put the laptop down, go get some beer, go get some tacos, and wait it out. When I scanned the primary body portion of my i8, I think it took about 5.5 hours to complete the mesh. I've recently seen people talk about exporting the point cloud and then having a third-party software do the actual meshing. I haven't done that yet, but it's definitely something I'm going to try pretty soon. So the Einstar works like any other 3D scanner by generating a point cloud, which is millions of data points all mapped in relation to each other, as well as their distance to the scanner. This means one of the most important jobs of the scanner is to recognize the points it's already scanned in order to build out a bigger point cloud. That's what we call tracking. Tracking errors are one of the most common challenges you're going to run into, and there's things that we can do to mitigate and improve that situation. One of the most common methods of improving tracking are these scan markers. They're basically round reflective stickers that give more features for the scanner to track, especially on a large flat panel. I really dislike working with these things. They're one-time use and they stick a little too well to automotive body panels, so they're really kind of a pain in the ass to clean up. So one thing that I found that's a little bit more convenient is to buy some 10mm by 1mm magnets. You get these off Amazon or anywhere like that, and you apply a marker to both sides, and they provide a nice, easy way of putting markers onto an object, magnetic object obviously, and then easily removing them because the marker on the other side provides a little bit of an air gap to reduce the magnetic force, so you can get it off the panel without making any scratches, which is kind of nice. However, this hasn't been much benefit to me because in my infinite wisdom, I'm working on a car that's almost entirely carbon fiber and aluminum. One last tip on markers, I like to apply them to a couple of sheets of paper. This is really convenient when you're going to scan something that's kind of small. You just put these down on the table, put your objects on top of it, and then you're going to be able to quickly and easily improve the tracking of the scanner for that part. So the Einstar comes with a calibration panel. I assume that all 3D scanners do. If it doesn't, I would probably be a little bit concerned. And this is really something that you're going to want to do anytime you're doing a scan that's going to be important. The amount of time and frustration that you're going to save by doing a calibration ahead of time is well worth the extra time that you're going to spend up front to go through the process. I've actually found even in some cases when the calibration is really out of date that the scanner will completely stop recognizing markers, which is kind of irritating. So the last and final tip on improved tracking and scanning is really almost kind of a cheat code. This stuff is Sublimating scan spray. The only one I've used is by Asub. They actually make 2 primary varieties, one in the orange can, the other in the blue. The main difference is the blue can lasts 1 to 2 hours, and this stuff lasts upwards of 12 hours. I highly recommend the orange stuff, especially if you're doing a large scan. This way you're guaranteed enough working time, even if you have a large point cloud that's going to take a little while to process. There's a lot of supposed alternatives to this stuff: dry shampoo, foot spray, baby powder with alcohol. If you at all value your time and sanity, I highly recommend a scan spray. If for nothing more, that the cleanup is non-existent. You spray it on, it evaporates or sublimates and is gone like it was never even used to begin with. And it really improves the quality of your scan. I really can't recommend this stuff enough. This channel is by no means sponsored by Asub, but I can certainly use a case of this stuff if you're so inclined. My first 3D scan was the interior of my i8. I wanted to design a MagSafe charger for someplace to put my phone. Out of the factory, it has this kind of useless cubby thing. You can't really put a phone inside. The door opens toward the driver, so it's really kind of a useless storage compartment. I used the scan data to create a MagSafe charger that replaced the storage compartment, and by doing so, I was able to make a part that fit really well without a whole bunch of trial and error. I utilized the factory mounting points, and this all just clicks right into place. You can see the resulting mesh from the scan. This was reduced slightly to make it play a little bit nicer with Fusion 360, but you can see the mounting points were picked up fine. This is where we attached our brackets to. These are steel brackets, And the way that the MagSafe charger mounts to the console is with some magnets that are glued into the backside. One thing to note, I actually have two different meshes in here. The first one is a little bit higher detailed. Let's bring in the triangle view. You can see that's the one I did the actual design to. And then as a reference scan, I have one with the factory lid, so I can see what the fitment was on that. And you can see by the number of triangles, it was reduced significantly to reduce lag when moving the part around. I'll bring that one back in. And the part itself was done with the forms tool. This was actually a little tricky to get the hang of. It's especially nice if you need to make something a little bit more organic shaped and your typical sketch, extrude, cuts, fillet geometry doesn't really play very well with it. And we can see on the back side where the magnets mount. You can see how the shape just flows well right into the console like it would from the factory. So I was pretty happy with how this came out. The scan itself came out pretty well. The part came out pretty well. Overall, just a really good intro project to using mesh as a design tool. So some of you might be watching and thinking, I'd really like to get involved in some of these design tools or fabrication methods that I see here, but it can be a really daunting process of trying to figure out where to start. If you're looking for high quality, well-produced content, you're probably not going to find it here, but I can highly recommend the folks over at HP Academy. They offer a really vast array of motorsport-centric courses, everything from engine building to engine tuning, how to build a wire harness, and then also just general automotive fabrication. More recently, they've released some content related to designing automotive parts in CAD, as well as 3D printing and 3D scanning in the motorsport space. They also make the process risk-free, because if the course content wasn't what you thought it was, or you're really not happy with it, then you can go ahead and request a refund. However, based on all the courses that I participated in, I think you'll be quite happy with the content. So check out the website link and the discount code and start your motorsports education journey. Here's another early project that I did. This is, by all accounts, a pretty bad scan of a BMW E34 M5 engine bay. In this case, the customer had an open cone filter that was attached directly to the mass airflow meter and didn't want to go through and source a factory airbox. So I ended up designing a aluminum carbon fiber airbox heat shield thing for him. When this scan was done, there was really no prep work at all. Didn't use scan spray. This was also done outside in direct sunlight. So I really had a lot of things working against me here. But for as bad as this is for being a complete nice looking scan, it provided all the necessary geometry to actually make a functional part. So we've accurately captured the round inlet portion of the mass airflow meter. We have the mounting slot, which we're gonna have a stud that the airbox attaches to the car with. We have the outside radius of the power steering fluid reservoir, and we can see where the radiator stops, where the frame rail starts, and any other obstacles that are in the way. And then down here, you can see the radius where there's a rubber bushing that the bottom of the airbox will mount to. All right, so all this should make a little bit more sense when we bring in our sheet metal body for the airbox. You can see I was able to notch out the aluminum for that pipe right there. Clear all of the critical components. And if we bring in the hardware, you can see I was able to design the right location for the stud. It's all using PEM hardware. Did a quick and dirty representation of the K&N air filter that he used. And then finally, we have our carbon fiber top plate. And we have an air temp sensor in the back of it. So while the scan itself leaves a little bit to be desired, I would have done this indoors with a fresh calibration and a bunch of scan spray. It ultimately did the job, and we got a nice fitting usable part out of the whole deal. So in this example, I used a scan to create the exhaust, and it was important that the exhaust had a junction point that was going to be easily compatible with whatever motor swap I decided at the time. When I did this, I hadn't yet decided that I was going to go with the rotary. I was exploring a couple different options, and I've since deleted a higher resolution mesh of this exhaust sealing area, but you can see I was used to design the hangers, which were done in sheet metal with 3 factory mounting points, everything lined up really well. You can see we're designing the support bracket for the factory downpipe and mating up to the factory turbo. This is actually a pretty simple exhaust design for the most part. One of the things that took me a little while to figure out was how to best translate the angles and cut marks into the actual bends, and this is what I ended up doing. So if you create all your mandrel bends on the same origin, then you can measure the angular relationship between the two. As you can see here, this is 110 degrees. We marked the mandrel bend with a 3D printed centerline marker. So in order to mark the angular relationship, you're going to need the radius of the tube diameter as well as the angle, and then the measurement that you're going to want is the chord length, which allows you to use a straight measuring device such as a caliper. In this case here, we have a 110 degree angle with a 1.5 inch radius, and then that gives us a chord length of 62.4 millimeters. We adjust our caliper to the required 62.5 millimeters, lay it over the tube, describe your line, and now you have an accurate reference point. I've used this method on a couple exhaust projects and it's been really accurate. I've been able to tack everything up off of the car, and then when I go to put it up, everything fits perfectly as intended. If there's any slight misalignment, that's going to get taken up very easily by anything that has a slip fit joint, like your mufflers or catalytic converters, X-pipe, what have you. Here's another project that involved scanning an interior part. This, again, was sprayed with the ASIP scan spray. In this case, the console was already cut for some gauges, but the customer failed to account for the fact that the HVAC box is directly behind the console, and then you can't actually mount the gauges in the car. So I was provided the console as a base to design an aftermarket gauge cluster for. So again, you can see where the Einstar does really well. Large object, picked up all the detail of the texture on it. You do lose some detail and resolution around the holes. As you can see, this was a reduced mesh as well, but ultimately we're able to design a cluster directed to that. It mounts with some tabs and some double-sided sticky tape. There was also a spot for a charging port. And the main shape, the interfaces with the console, was done with the forms tool, and then that was merged with some solid bodies to hold the gauges and mesh everything together. And then this is how the final part ended up looking. Fit really well, and customer was really happy with that. So we're going to jump to Xstar, which is the Shining 3D software in support of the Einstar. And this is the biggest 3D scan that I've done yet to date, and I wanted to show a couple things that you might want to look out for when you do something this big. The most important one that you're going to see is on the side here, where this entire scan is made up of multiple projects. And what this is going to do is allow you to limit the amount of point cloud data that you capture. If you try to capture all of this in one project, it's really going to bog your computer resources down, and the software will more than likely crash. And that's really kind of user error rather than a fault of the software. So you want to break your project down into a bunch of smaller scans that are all combined with the align feature. So you can see in highlighted blue is project 1, project 2, 3, just to give you an idea of how much of an area that I would scan at once. One of the really nice things about doing this is that you can export all of these projects individually, and they will export on the same origin. So if you want to export the exterior body panel and reduce the mesh by a significant factor because you're not designing anything off of it, you're really just using it for a visual reference, you can save on a whole lot of pain and suffering in Fusion 360 by reducing the triangle count. But if you are using the suspension or want to develop brackets or anything in here, you can export this at a higher triangle count and have your higher resolution Fusion 360. The other benefit besides the resolution control of exporting multiple bodies into Fusion 360 is that it gives you ability to hide certain sections of the mesh that you're not currently using, rather than having to bring the whole thing back in and out of view. One thing to always keep in mind is Fusion 360 is pretty awful at processing mesh data, because the way that it works is it's basically one giant single-threaded math problem. and all those triangles need to be recalculated every time you move the part. Ideally, you want to keep the resolution to the mesh as low as possible for your intended use case, and then also hide the mesh whenever possible. And the reason that you're going to want to be able to hide sections of the mesh is if you ever try to do a section analysis through a mesh in Fusion, that ends up being a pretty laggy and resource intensive operation. Next, we have the scan of my Borg Warner 8374. I have a link to an Etsy download to the STL for this. I was kind of annoyed that I couldn't find any pre-existing models of the Borg Warner Turbo, and Borg Warner themselves don't put that information out to the public, which is really irritating if you're trying to design a turbo kit and you're really not sure on fitment. So I had to go and spend like $2,000 on a turbo, scan it, and then design everything around it. So here was the resulting mesh of the turbo scan. I was really quite pleased with how this came out. This was done by merging a couple different point clouds. Scanned the turbo from a couple different positions. This was fully sprayed with the ASIP scan spray, and you can see the type of detail that you should expect. All the bolt holes for the wastegate actuator, Borg Warner logo. You can see a couple voids in dark recesses, which is kind of unavoidable with an IR structured light scanner. But short of spending $15,000 on a laser scanner, I am pretty happy with the results that this gives. The last scan we're going to check out is a kind of a neat project by a local dude, Marvin, who goes by Chillmatic on social medias. I'll link to his accounts below in the description. He's doing a unique project with a Fiat 126 and a GSXR 1000 motorcycle engine in it. It has Mazda Miata suspension in the rear, and he was questioning the geometry of the cantilever links for the shock mounts, and I offered to scan the car to give him the advantage of being able to work with this in 3D and save a little bit of time and money while he figured out the rest of his suspension. So taking a look at the Fiat Scan in the Xstar software, this is actually the first time that I use the latest beta release of the Xstar software, and they made a lot of good changes. The first of which that I really like is support of the 3D connection space mouse, so you can freely rotate things much easier than you could before. I really like that. Other things that have changed is that you can actually change the scan resolution in the middle of the project. So I went against my previous advice and created this under a single project, mainly to test out how the new software update does. And it actually improved quite a bit. I was pretty amazed that I was able to get this far in the scan and not have crazy lag during the scan process. Here you can see a good example where there was a tracking issue and picked up a double fender flare. Same thing on the tire. There's still a slight misalignment there between the outer scan and the inner scan. And this is another reason why it's beneficial to do multiple projects. In this version of Xstar, they did introduce an undo button. Previously, if you got a scan error like this and you had it as a single project, you were stuck having to delete this section of the point cloud, or if you really messed up, start over. In this case, we now have a back button, which isn't visible in this screen, but that's going to be really useful. I did encounter trying to use the back button that it did seem to stall a bit in the software, so there's probably some additional work that they have to do there, but overall you can see that the scan itself did pretty well. Picked up the details of the shock mounts, cantilever brackets, and the motor really well. And then I also did another scan of the underside and the front suspension that we'll take a look at in Fusion 360. So here we have both the bottom side scan and the rear all lined together in Fusion 360. And because the original intent of this scan was to help facilitate measuring the suspension geometry, and this car happens to use Mazda Miata suspension components in the rear, quick search on GrabCAD yielded that both the front and rear suspension parts were available for download in step file format. GrabCAD can be a really great resource to obtain models that other folks have done and uploaded. You also do need to utilize a little bit of caution, because for every good model, there's probably 20 others that were an upload of what looks like somebody's university homework assignment.
The maxim is, dovii no provii, trust but verify.
But in this case, a quick drop-in of the Miata suspension off GrabCAD lines up really well with the scan. I didn't spend too much time aligning this. This was really just to create a fusion project and get this guy jump started with working with this. So not only is that going to help him design the links in the rear and model the motion thereof, but that also allows him to look at the front and start establishing ideas for how to deal with the front suspension. And just because we have the Miata front suspension available to us, we're able to locate that into place and narrow up the upper A-arm pivot to approximately where it could be on the car. And you can immediately see right away that this is not going to be a suspension option for this car. Due to the way the front's laid out, it's probably going to be some sort of McPherson strut setup. This is where having a 3D scan of whatever you're trying to work on can save you a boatload of time up front. So rather than browsing eBay for stuff that might fit or trying to buy used stuff off Marketplace to try to do some physical mock-up, you can find a buddy that's got a similar component, 3D scan that, or download some potential models to play with, and then you can understand what can actually fit in the car without investing any time in real parts that you might have to resell and take a loss on later. And then while scanning this car, in conversation it was mentioned of how much money he had spent on McMaster car components, and some of which were some trial and error fitment. And that's another nice feature with Fusion 360, where if you click insert, you can directly download McMaster car parts, because that's a really impressive supply website that has 3D models of just about everything they offer. Hardware to spherical rod ends to all sorts of fabrication stuff for linkage that you might want to use. So this is a really great tool to use if you haven't already discovered it. If you made it this far, thanks for watching. In the next episode, we're gonna make the oil pan for my 13B i8 swap, and it's not gonna be 3D printed, but it's gonna utilize one of my favorite construction methods, which is laser cut parts that are welded together. See you next time.